Hi there, welcome back. Today we've got a Nordmende EM 3366 FET VOM volt ohm meter. I've been looking for one of these for some time, and a friend of mine who I met through the channel, he was a subscriber, and we've subsequently met, and he's actually visited Madeira. He lives in Germany, and he actually found it for me. He knew I wanted one, and he helped me out, and I really appreciate it. Now, this thing is a FET voltmeter, so it's a very high input impedance, and that is important because it is ideal for valve radio, tube radio restorations, especially when it comes to alignment. The other factor which is very important is that it's got a zero center, or center zero mark over there. So if you're measuring volts, you can, or milliamps I presume as well, you put it on the center there, and if it's positive it deviates one way, if it's negative it deviates the other way. And this is very important when you're doing the adjustment of the final IF stage on FM in the tube receivers, because you're actually balancing the final discriminator part of the coil. So what we have here is we've got the selector switch, which gives us off battery, DC voltage, AC voltage, milliamps and ohms. There's also a reverse DC, in other words negative DC selector. The selector switch, the range switch at the top, gives us ranges which for the case of voltage goes from 0.1 volts to 1000 volts. In the case of milliamps goes as high as 10 amps, in which case you've got a separate input over there. In the case of resistance you can go up to multiplied by 1 meg. We've also got the adjustment for the ohms, for the ohm measurement, which uses an internal battery obviously. That's why you have the battery check over there, and you can adjust that before you do your measurements. You also have a ground. This is chassis ground over here, and this is the adjustment for that center zero, so you can zero the meter whenever you want or apply the center zero function. It also has the input here, which is a BNC socket, and this thing did not come with the test leads, so I'll have to build one up on there. Now the condition of this thing is incredible. It really looks very, very new, and there are very few marks on there. The ones that are there are obviously from use, but there's been no damage. And I've also got the service manual. Now my friend Derek went one step further beyond finding me this little treasure. He actually translated some of the service manual into English because it's from German. So this should be quite fun. Now the reason I'm doing a quote-unquote restoration is because I have tested some of the functions and some of them aren't quite there. The battery was leaking when it was bought, so that was removed. So I'd like to go through this, perhaps do a recapping, and then check the function and then do the calibration so this thing can become useful on a day-to-day basis over here. So let's get started. Hope you enjoyed this, and at the end we'll do all the testing and see if we've got somewhere. Let's do a quick check for accuracy. I've got this set up for AC volts. I've got the Bryman Big Brother in parallel with it just to compare. I've got my signal generator producing 100 millivolts RMS at 100 Hertz, and I'm going to first of all try to zero this. Now as you can see, it's having absolutely no effect. Got this on the 1 volt range, switch it on. So we've got no Hertz over there because it's 100 millivolts. Too low for that thing to detect the frequency, but it's 100 Hertz. That's reading 98.9 millivolts RMS. And here we've got something. Now if I go down to 0.3 volt scale, it's a bit more. If I go to the 0.1 volt scale, I'm actually getting 0.035. So there's obviously something wrong with this. Let me put it on 1 and increase the voltage. That's 200 millivolts RMS, 300, that's gone up to 5, 1 volts RMS, We're now starting to see the 100 Hertz there. And all I'm getting here on the 1 volt range is 0.3534 volts. So there's something wrong with the AC. That has no effect. That has no effect. So the AC is a bit buggered. Let's try DC. Now for DC, I've connected it to my bench power supply. 0 volts. I'm going to switch this on to DC volts. We should be able to, yep, that works. That is perfectly zeroed, looking at it straight on. It's slightly off on the screen. And I'm going to give it 1 volt. 1 volt. And what we see here is just under. We've got 9.65 or so. So it's slightly off. If I go to the 3 volt range, it's giving me just under 1 volt. 10 volt range, it's actually on 1 volt. Let me increase the voltage to 10 volts. There we go, 10 volts. Again, we've got 9.8 or so. So it's just slightly off. If I go up to 20 volts, put this on the 30 volt range. If I go up to 20 volts, it looks pretty close, just under, and 30 volts. Again, it's at 28.5 or so, so it's just under. So as far as the DC voltage range is concerned, it's just under. And I'm sure that can be very, very easily adjusted. So the problem seems to be solely with the AC voltage so far. I haven't tested the milliamps yet, but the milliamps I'm not really worried about because I'm not really going to be using this to measure current. What I'm going to do next is open this up. I'm going to put a battery in there, see if the ohms range works, and try and figure out why the AC is not giving us the right readings. Now, taking off the top cover is very, very simple. There's 2 screws at the back and the cover sort of flips out like that. And it looks pretty clean inside. We've got the board, the main board over there, the switching in front. On the lower end, inside, we've got the power supply, just the transformer, with the mains coming in through the fuse. And we've got the battery compartment there, which is a little bit buggered with a bit of corrosion. So I'm going to keep dismantling this a bit more. You can take the side panels off just by themselves. And just to see what we can see without actually removing the whole board just for now. Now the way this is done is actually quite clever. There's a framework and panels screw on. So you can literally open up the whole thing, as you can see. And I've got pretty good access without actually having touched the electronics. Well, I'm going to take out one more thing, which is this shield panel over here, which just unscrews off the sides here. There's one solder connection here, which I'm going to unsolder, and then I'll be able to pull this off, so we'll be able to look at the top of this. And who knows, perhaps this whole thing can be maintained or repaired without even taking the boards out, which will be great because there is quite a concentration of wires, especially in the switching over here. And you've got to be very careful with this because if you break one of those wires, a lot of heartache, try and find out which one. So the idea is to try and do it with as little intervention into the wire parts, into the rat's nest as possible. So that's what I'll do next. Actually, the 2 more wires, 3 more actually, that need to be unsoldered because it goes through that shield, and that is the AC supply and a ground. And here we go. We have access to the top boards. There's 2 boards over here. And that one. That there looks to have been added on. That Vera board thing there is a bit weird. The rest seems to look original. Getting access to the underside is a different story, but who knows, we may not need to. Now I'm going to get the schematic out and start tracing some of this and see what's coming in, what isn't. I'll probably have to solder the, in fact I will solder the transformer leads back in there. I'll get back to you when I find something. The easiest way to figure out what's happening in a circuit like this, where you've got a lot of switching going on, especially with the complexity of switching that you'll get in a typical multimeter like this one, is to actually draw the signal for a set of conditions, which you determine. So I know that the DC measurement is working more or less okay, slightly off in terms of the maximum reading. So I'm going to follow a DC signal, and I'm going to assume that I'm setting it to the, well, let's call it the lowest range, 0.1 volt DC. Positive polarity. What else can you choose? Not much. So let's follow that signal. Comes in here, goes up there, goes to here. Now it's going to look for the DC voltage switch, which is that guy over there. So it comes across here, it goes to there, and it's in the 0.1 volts, so it's in the 0 position, or rather in the lowest position. So I don't have any resistive divider going on, so it goes straight across to there. If I look down here, all this is over here is a potential divider, so that the higher my voltage is, the lower down I'm going to collect it from. In other words, if it's on the lowest range, which is 0.1 volts, I'm not dividing it at all because I want that maximum signal to go through. So this whole thing here is just that potential divider. If you look, it's connected to ground over here, which goes across here, there, and to the ground of the signal. That same ground comes along and it becomes ground over here. So far, what have we got? We've got the signal up here going up to there. That is the same switch for DC voltage. It goes to there, goes up here, goes across there, down here, and it's going into that FET. That FET is what's giving it the very high input impedance. Now, what does my signal do? Well, it comes into the FET and it's meeting a differential amplifier. So the signal effectively goes into the FET and it's going to come out as two signals. The differential amplifier situation is here. There is an adjustment over here which is preset according to them by the factory. This P1 is the setting for the 0. In other words, you can balance this differential amplifier. If you've got 0 volts, what you do is you adjust this P1 so you get 0, and the two output signals from this differential amplifier is that one and that one. So let's follow that. That's one, goes to there, goes to there, goes to there. Now, where does it go to from here? Well, it can't go along here because that's going nowhere. It's got to go up here, which means it goes to that switch or that switch. That is the polarity reversal switch. And because we've got it set on positive polarity, it's going to be as it's set there. So it goes there, 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 and there. Where do you go, my boy? Where do you go? Well, let's leave it there for now. Let's follow the other one. This one that comes out of here, goes to there, goes to there, goes to there. I have it going up to here for positive polarity. That's your adjustment on the positive polarity to get your calibration done. That goes to there, and to there. And this guy here comes to there. I'm trying to figure out which switch this is. That will be the range switch, but or is it? No, it's DC voltage switch, so it's off 1 2, off 1 2. So it's that guy over there. Okay, so that's adjusted with the range switch, so that one will go there, there, and bang to the negative of the meter. And similarly, that one will go to there, across to there, and it's the positive of the meter. That's our positive DC voltage. Now what have we learned here? Well, we've learned that we are getting DC voltage measurements. They are slightly off, and you can adjust it with R78, which is that guy over there. And in the negative polarity, they tell you to do the same. And if you have negative polarity, you would adjust R79. You would also adjust P1, which is your zero needle setting. So you can set it to 0 or move it up to the middle of the screen if you want it, if that's what you want to measure. In other words, if you want to use that positive or negative deflection for 0 volts. And all that seems to be working. So we have figured out that this differential amplifier over here is working. What else have we learned? This over here, P2, only applies in the last range, which is resistance. So P2 is obviously the that setting for the resistance measurement. So that makes sense. And that's all that's in line with for DC voltage. So it seems. The only other thing would be this potential divider down here, which is related to your different voltage ranges. So that's really it for DC volts. There is your signal path. Brilliant. Now doing exactly the same thing for an AC voltage. So let's assume we're measuring AC volts and we're setting it to the lowest setting, so 0.1 volts AC. Let's follow the signal. Comes in there, goes up there, it meets the function switch, and we're looking for AC volts, which is that one over there. So if that is closed, it goes to there, it goes to there, and it meets this capacitor, which makes sense. This will be a DC blocking capacitor. It goes to there, and here you'd meet the range switch. Again, the same as the other one. 0.1, 0.3, 1, etc., etc., etc. So, the reason you have these capacitors here, these trimmer caps, is you're trying to do a potential divider, and the potential divider is not only resistive, it's capacitive as well. So because you've got that capacitor there, you'd have to compensate with those fixed caps and trimmer caps over here. So the idea is that you get a capacitive divider for a higher frequency than just, well, DC. And you wouldn't be measuring DC on an AC setting. It wouldn't go through that capacitor at all. So this capacitor and all those capacitors and trimmers there are to make sure that this thing is flat to as high a frequency as possible. And I believe the highest frequency is 1 meg. Well, we're not too worried about that. We're just trying to get the function working. So we'll assume it's set flat. And let's assume we're using a 100 Hertz or 50 Hertz signal anyway. So that shouldn't be a problem. So the signal will go across here because that's the lowest setting we have, 0.1 volts. If you look down here, this just ends. It's just the collector point for this whole switching here. So we've got it over there at the moment, and we take it from here, and it goes up, and it goes across, and it goes down, and it goes into this JFET. And this JFET is what gives you the high impedance. Now, it's not as high as input impedance as the DC is. It's about 10 megs. The DC is about 50 meg. And that has to do with this potential divider, the values of this potential divider. Because I suppose technically the input impedance of that thing is, call it infinity for now. But the values of this potential divider aren't as high in resistance as the DC chain because you want to keep it flat across the frequency span, the bandwidth that you want to measure, and therefore these capacitors are in place and you have to use reasonably sized capacitors, so you use more reasonably sized resistors. So 10 megs, pretty good. Okay, so our signal is now over here. What happens to the signal from here? Well, if you look at this, if you follow it in a very rudimentary way, the signal goes there, it goes there, it goes there, 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 and really it actually goes to there and meets this capacitor. Through this capacitor, DC blocking goes to there, and this thing will send us to that top one, which is the lowest range. And I'm just following the signal here. This signal now goes up here, across here, across here, across here, another DC blocker, and a ground reference resistor, and it goes back into here. So what we've done is we've pre-amplified it, sent it through another series of range selection, range level setting, and it goes back to the amplifier again, and it goes back in here, back in there. I'm just trying to see where the signal's going. Signal is really following that to there, and there's another DC blocking. So that's telling us, and here it is, we've got a level control. R83 would probably be, I'll have to check the service manual, setting a level, in other words calibration. It goes through the calibrating pot into here, so we've got another level of amplification, and up to here, up to there, up to there, and suddenly we meet two diodes. This is starting to make sense. This is AC over here. We want DC. So this diode would rectify the one half of the waveform and bring us the signal to there. For the other half of the waveform, and bring the signal through here, and we have R80, which will probably be again calibration. So we've got the two signals which should go to the meter coming out of that. This is a low frequency, they call it a low frequency amplifier if I'm not mistaken. And well, let's just take these guys to a more accessible point, to there, and also this one to there, and this then comes up here, and if you remember, this is the AC volts, so it's that one there, it would go across there, and boom, we are now measuring. That's one side of the meter, and this here would be the other side of the meter. That's how we measure AC volts. Now, what have we learned here? Well, first of all, rather stupidly, I said you couldn't adjust the zero on the meter. Well, that's over here, that's for DC. You would set the zeroing of the meter with these other calibration pots over here, that one, probably that one, and where's the other one? There's another one here, that one there, and there's another one here. So you set the calibrate, you calibrate it with these three pots, whereas with DC, you're balancing the differential amplifier. And it's on DC that you can use the zero center meter. And that's how you get your AC voltage. So, since the AC voltage is not working, and the DC voltage is, we know that this entire part of the circuit over here is working, and the problem is this part over here. So it's now become easier to trace the signal. I'm going to feed a sine wave into here, and I'm going to do exactly what I've done here. I'm going to follow this on the board and see if and where I lose the signal. Obviously, it could be something as simple as the supply not getting to this line over here. That line over there is the positive supply. Comes from the regulated supply over here. And if we just have a quick look at the supply, just for interest's sake, we know it must be working because it's feeding a voltage across that line to there, up here, and it feeds this differential amplifier. So that supply, and that's ground over there. There's your V plus, there's your ground. So that's getting to the differential amplifier. It does not mean that it's getting to this part of the circuit, because this could be a link that's broken or something similar. There is some signal getting through, so perhaps it's not that. But just to look at the voltage regulator, what you have here is AC coming in. This is wired for 220 volts. As you can see, the two halves of the primary are in series. I presume you can use this on 110. You just put those in parallel. Your secondary comes out. There's a resistor and a neon, which is that little green neon on the front, which makes sense. There's your bridge rectifier, ground down here, positive up here, filter cap. There's a Zener diode here, which I'm not sure, I don't remember what it is. I think it's a 10 volt Zener, if I'm not mistaken. Just trying to remember what I saw on the other page. It's here somewhere. But that's a Zener. That sets a reference voltage based on that Zener. There's another resistor to another Zener, which basically that drops part of the voltage, that drops the other part of the voltage. It goes to an op amp. The op amp works with the feedback line over here, which takes a sample from the output voltage, in other words, the final rectified voltage. It samples it, feeds it back in here, and this op amp regulates the opening and closing, or rather the feed through that it allows to that transistor, which is the pass transistor for this regulator. So this you can adjust with this pot to get your 9 volts. And that seems to be working too, or we wouldn't have the differential amplifier working. Now obviously there's a lot more that I could check. I could check the DC amps, I could check the resistance levels, but until I get this part working, I think I'll just focus on this part of the circuit, which I know is got a problem somewhere. Let me have a look at that. Okay, it's report back time. I started off fixing up the battery at the back, removing it, cleaning it out, took out all the rust, not the rust so much as the corrosion. And if we do that now, we can see the level of the battery, which seems okay. Now, the other thing I did was, before starting, I set the needle to absolute mechanical 0 with that little adjustment in the middle there. You do that with the meter off. And what I found was the power supply, there's an adjustment for 9 volts. It was just slightly high, so I brought it down and set it to exactly 9 volts, and it stayed that way. The capacitors and components on the power supply seem to be all fine, so nothing was done there. So let's go to DC volts first. Now, what you need to do with DC volts is you need to be able to adjust this 0 set, and the reason is you set it on 0 there, or you can set it on center 0. Now, I was getting it up to there when this trimmer pot, or this pot, was on maximum. And if you look at the circuit, what you see is an adjustment, a balance adjustment in this differential amplifier. You also see that when you adjust this pot here, you are giving the one side of that bridge more resistance and the other side less resistance. So obviously something was out of balance with the fixed resistors on there, and I decided to do a bit of experimentation. What I found was that if I dropped the resistance on the one side, I could have either increased the one side or dropped the other side. It's much easier to drop by simply putting another resistor in parallel. And I found the ideal one to get this type of scope, this range, was to put a 10K resistor in parallel with that 910 ohm resistor. And now we get this thing moving quite well. So I've zeroed the meter and I've put in 100 millivolts and I've got it slightly over the top. So all I need to do here is to adjust this pot over here ever so slightly. And I'm on 100 millivolts there. If I bring this down to 50 millivolts, I'm just under. So it's not absolutely linear. See there, it starts getting very, very accurate. Now what we can see is that it's not absolutely linear. That's supposed to be 20. It's giving me 17.5. Now what I think this is, what I believe this is that the transistors in there are no longer acting as matched pairs. They are supposed to be perfectly matched, and I don't believe they are anymore. So not particularly linear, and I believe I'm going to have to find transistors to replace that, but I'll get back to transistors in a second. What this means is that if I put it on other ranges, we're at 1 volts. Go down to 0.5, we're just over. It looks more over on the camera, but we're just over. And if I put this in here, just to confer, 0.5 volts, that's what we're feeding it. That's what we're seeing on there, 0.51 or so. So we've got a linearity problem with that differential amplifier, and I believe it is the actual transistors, and they're not that easy to find. So I had to make a decision. I had to really decide what it was that I wanted to achieve here. And what I want to achieve here is to create a high input impedance meter, mostly to measure volts, AC and DC, but mostly DC to align radios with. This is not supposed to be a very accurate multimeter. For that I've got Big Brother and I've got Little Brother on the shelf there. So you can get an endless number of really cheap multimeters, digitals, that'll be more accurate than one of these, unless you really go to town with setting this up. So I didn't want to go to that extent. I want to get this thing working. So whether it's 0.5, 0.51, I don't care. So far we've got the DC working fine. Now the AC is a bigger problem with the alignment. And the reason is that for AC alignment, this thing is really weird. Let me connect an AC signal source to here. Now, they tell you to connect a 50 Hertz, 100 millivolts signal, AC voltage, to your meter. See, now I've switched it on. I've got 100 millivolts, 50 Hertz sine wave on there. They say you're supposed to adjust 3 different trimmers to get this thing to calibrate properly. One of them is R83, the other one is R82, and the last one is R80. Now, one of them is sort of the preamplifier stage, the other one is the level stage, and the other one is the linearity stage. And I'm finding it very, very difficult to get this thing to be linear as well. And I'll show you. If I put this at 50 millivolts RMS, it's pretty good. Now if I go down 40, it's 38, 30 is 26, 20 is 16, 10 is 6. So I've got a linearity problem. When I get to the top, it gets better. 70 is 71, there's 90, there's 100. So again, this thing's not linear, and I believe it's the transistors. The capacitors were all pretty high ESR, so I've replaced them, the electrolytics, and once again I'm going to leave this as is because it's doing the job that it's supposed to do for my purposes. What I'll be using this for is to measure AC audio levels across the dummy load or an actual speaker. So I can get very low voltage levels, contrary to the ones that I've already got here. And I'll be able to see the meter action and be able to determine maximums and peaks and minimums and so on, which is exactly what I want this thing for. So that's good for now, but like the DC situation, I'm going to have to find transistors and FETs to try and get matched pairs and replace it on here just to get this thing more linear, and that'll be for a second stage of the project. So then we have milliamps, and with milliamps I'm not going to pass a current through this, but what it does is it basically measures the DC voltage across the resistors that you adjust as you set the range. So that works with the DC voltage measurement. And the next stage, of course, is resistance. Now, when you put it on resistance, I've shorted the leads here, and I unshort them. Now, when you put it on resistance, you make two adjustments. One is you make sure this is on 0, and 2, you unclip it and you adjust the infinite with that control till you adjust the end to infinite resistance over there. And then it's just a matter of putting resistors in place. Now this one here is, what is that, 470 ohms I think it is. 470 ohms. The resistance line is that one there, 4.75 more or less. Just under 50. That's 470 ohms. Pretty good. If we take another one, we take, what is this? 47 ohms. Okay, let's see what that gives us. 47 ohms. 47, I suppose. Let's see if we can get a better reading here. Just under 50. Yep. It's close enough. It's no big deal. You don't want you don't get particularly accurate readings with this, but it's in the ballpark. And again, it's using the effectively using part of the DC voltage amplifier. So what have we got here? Well, we've got a FET VOM, which gives us okay readings on DC volts, not too badly. Not particularly linear, especially on the lower end of the scale, but it gives us DC volts. It gives us negative DC volts if we invert that there. It allows us to adjust the needle to get center 0. So that's perfect for aligning the discriminator part of the IF transformers in FM radios, which is what I want it for, so I can get deviations left and right of center. It allows me to measure AC volts with very low readings, very low scale, from 0.1 volts to, what is that, 1000 volts. I particularly need this in the lower ends here to get low levels of AC, especially audio. Again, used mostly when aligning tube radios, both the IF alignment and the RF alignments. So that works fairly well, although again, not linear. I can do resistance measurement just for fun, and I don't want to even try the current measurements because, I mean, it does measure some very, very high currents, 10 amps, but I've got better stuff to measure that with. So basically that's it. We've got a project which is not complete per se. It needs some serious work with some serious semiconductors, and they are seriously difficult to get. So I have set this up in a way that I can use it. I use it mostly for indication, peaks and so on, so I don't need absolutely exact readings, so that's fine for me. But I won't give up on this. I'll look for those components, and when I do get them, I plan to do a complete revisit to this project and get this thing really back to where it should be. Well, I hope you've enjoyed that, and I certainly have. And if you did enjoy that, click like, subscribe, share, and all that jazz. And if you want to support the channel, please do so on Patreon. Thanks for watching. Bye for now.